From nothing, everything was born. But was nothing ever truly empty? Nothing, at first glance, seems straightforward, but defining it proves to be surprisingly complex. Our universe began from what appears to be nothing, but what does that truly mean? Is there a state of absolute nothingness, or does nothing itself have some form of hidden existence, a backdrop from which something can emerge? And where did this nothingness come from in the first place? Long before modern science tried to unravel the universe's mysteries, ancient philosophers were already pondering profound questions. What does it mean to exist? Could there ever truly be such a thing as nothing? One of the earliest and most influential thinkers to confront this paradox was Parmenides of ancient Greece. He proposed a radical idea: nothing cannot exist. To him, the very concept of nothingness was contradictory. If something genuinely did not exist, how could we even conceive of it, let alone describe it? Parmenides argued that existence has no beginning or end. It simply always was. He believed the universe was eternal, unchanging, and never created. Because if there had ever been a moment of absolute nothingness, how could anything have ever come into being? His perspective challenges us to reconsider our assumptions. If nothingness is truly impossible, does that imply that the universe has always existed in some form? However, not everyone agreed with Parmenides. Even in his time, other great thinkers grappled with this paradox. Aristotle, another legendary philosopher, viewed nothingness differently. He didn't see it as a contradiction, but as a kind of potential, a blank canvas from which new things could emerge. Imagine an empty canvas before an artist begins to paint. For Aristotle, this emptiness was not truly nothing, but a space full of possibilities, a foundation for creation. He believed that even if a space seemed empty, it still held the potential for existence. For centuries, philosophers and scientists have debated these ideas. Can absolute nothingness exist? If the universe originated from nothing, what kind of nothing are we talking about? These questions challenge the boundaries of human thought and force us to rethink everything we believe about reality itself. In more recent times, thinkers like Immanuel Kant began exploring the limits of human understanding. He posed a profound question: could absolute nothingness, the complete absence of everything, be something beyond our mental grasp? Our entire existence is shaped by a world full of matter, space, and time. Things we can touch, see, and measure. But Kant argued that true nothingness, where absolutely nothing exists, is beyond our imagination or comprehension. It's a concept so foreign to our daily experiences that it feels out of place in our understanding of reality. This leads us to a deeper question. Could it be that absolute nothingness doesn't actually exist? Or is it possible that what we perceive as nothing is, in fact, the source of everything around us, the spark that ignites creation? These are the questions that have puzzled humanity's greatest minds throughout history, leading to one of the most profound mysteries of all, the birth of the universe. Fast forward a few thousand years, and our understanding of nothingness has evolved dramatically. While philosophers pondered these deep and complex questions, scientists quietly worked in the background, using mathematics and experiments to uncover the universe's secrets. And this is where the story becomes even more fascinating. For centuries, scientists believed that space, the vast expanse where nothing seemed to exist, was exactly that, nothing. A vacuum was thought to be a void, an emptiness devoid of matter or energy. But in the 20th century, this perspective was turned on its head by the revolutionary work of Albert Einstein. His theory of general relativity showed that space and time were not separate entities, but interconnected, forming a flexible fabric that could bend and stretch in response to mass and energy. This was a groundbreaking idea. It revealed that space wasn't just a passive stage where events unfolded, but an active, dynamic participant in the universe's unfolding drama. The real revolution in our understanding of nothingness came with the advent of quantum mechanics, a branch of physics exploring the smallest building blocks of reality. Quantum mechanics revealed the bizarre truth: even in the emptiest parts of space, where nothing appears to exist, there is still activity. Imagine a perfect vacuum, a space devoid of matter, light, or any detectable presence. Even in this seemingly empty void, something extraordinary is happening. Tiny bursts of energy spontaneously pop into existence and vanish just as quickly. These fleeting events are known as quantum fluctuations, minuscule, rapid fluctuations of energy that appear and disappear in the blink of an eye. It's as if the universe is constantly buzzing with activity, even in the voids where nothing seems to be. These fluctuations are so fast and tiny that they are invisible to the naked eye. Yet their effects can be measured. It turns out that even in seemingly empty space, invisible fields are at work, constantly fluctuating like ripples on the surface of an ocean, creating virtual particles that appear and vanish almost instantly. This astonishing discovery challenges our understanding of nothingness. If even the emptiest space is alive with potential energy and quantum activity, then is it really empty? Could these constant fluctuations be the key to the birth of everything? Is it possible that the entire universe emerged from one of these quantum fluctuations, a burst of energy that expanded into the vast cosmos we see today? This mind-bending idea forms the foundation of modern cosmology. If quantum fluctuations can create tiny bursts of energy in a vacuum, could they also explain how the universe itself could arise from what appears to be nothing? This challenges our deepest assumptions about nothingness and existence. The concept of nothingness has fascinated humanity for centuries, from the ancient philosophers who pondered its meaning to modern scientists uncovering its complexities. Once seen as a lifeless void, we now understand that even the most seemingly empty space is teeming with potential. The quantum world reveals a reality where nothingness is alive with fluctuations, possibilities, and energy waiting to burst into existence. While science and philosophy have given us incredible insights, the true nature of nothingness remains a profound mystery. But this very mystery is what makes the universe and our place within it so extraordinary and captivating. Perhaps the greatest story ever told is the one that begins with nothing, leading to everything we see around us. In the smallest fraction of a second, the universe expanded from a point smaller than an atom to something billions of times larger. This expansion didn't occur in a specific direction. Instead, space itself stretched, carrying everything within it. The Big Bang marked the birth of time, space, and all that exists. But that was merely the beginning. The real mystery lies in what happened next. How did that initial burst of energy, this extraordinary explosion of space, transform into galaxies, stars, planets, and all the components of the universe as we see it today? To unravel this, we need to delve into the timeline of events that followed the Big Bang, examining each critical moment that shaped our cosmos. From the universe's very first moments, cooling processes began to take effect. Clouds of gas formed, stars ignited, and galaxies started to take shape, each one a colossal collection of stars and matter drifting through the ever-expanding universe. Over billions of years, these stars and galaxies evolved, creating the intricate and diverse cosmos we witness now. The transformation from an unimaginably tiny, hot point to the vast, complex universe we inhabit today is one of the most astonishing stories ever told. To truly grasp how the universe evolved, we need to break down these events moment by moment, examining the tiniest fractions of a second in the early universe. Monumental changes occurred in almost no time at all. Understanding these brief yet extraordinary moments is crucial to comprehending how everything began. Let's start at the very beginning, during the Planck epoch. This was a period so early in the universe's history that it defies our imagination, occurring less than a trillionth of a second after the Big Bang. The universe was then incredibly small and unimaginably hot, with temperatures exceeding 1,000,000,000 degrees. In this extreme environment, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single force. This unification is something we struggle to fully understand, because in today's universe, these forces operate independently, but during the Planck epoch, they were merged into one. What does this mean? Essentially, everything we know about physics, all the laws that govern the universe, were condensed into a single unified force. However, this era remains a profound mystery. Our current physical theories, including Einstein's general relativity and quantum mechanics, fail to describe what happened under such extreme conditions. It is as if we are trying to assemble two puzzles whose pieces simply do not fit together. During this time, the universe expanded at an extraordinary rate. Space itself seemed to stretch at a speed beyond comprehension. However, the universe was so hot and dense that light could not travel freely. Everything was shrouded in a kind of cosmic fog, preventing us from directly observing this early period. As the universe continued to cool, though it was still millions of times hotter than the core of the Sun, significant changes occurred. The first major shift was the separation of gravity from the other three forces. This marked the beginning of what is known as the Grand Unification Epoch. During this era, electromagnetism, along with the strong and weak nuclear forces, remained unified while gravity started to act independently. Then came an event that transformed everything: inflation. This explosive phase of rapid expansion occurred about 1/70th of a second after the Big Bang. Unlike anything before, inflation caused the universe to expand faster than the speed of light. While this might sound impossible, it is important to remember that it wasn't matter moving through space at this speed, it was space itself expanding. This rapid inflation stretched the universe from subatomic scales to macroscopic sizes almost instantly. Imagine something growing from smaller than an atom to billions of times larger in the blink of an eye. It is nearly impossible to fathom, yet this is precisely what scientists believe happened. Why did inflation occur? The exact cause remains uncertain, but many scientists theorize it was driven by a special form of energy known as the inflaton field. This energy created an immense pressure, forcing space to expand at a breakneck pace. As the universe expanded, it also cooled, allowing the once unified forces of nature to separate. In these early moments, the cosmos was a seething cauldron of energy, a chaotic quark epoch where quarks and gluons, the foundational building blocks of protons and neutrons, surged in and out of existence. Stable matter could not yet form. Instead, reality resembled a frenzied quantum soup where particles collided, appeared, and vanished in an endless dance. As cooling continued, quarks began binding into protons and neutrons, and within the first 10 seconds of existence, the stage was set for the next transformation. Photons, particles of light, became prominent, yet the universe remained a foggy expanse. Free electrons and protons scattered light, making space opaque. Then came a pivotal era, nucleosynthesis. Atomic nuclei of hydrogen, helium, and trace lithium formed, sowing the seeds of future stars. Hundreds of thousands of years later, the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. This recombination phase turned the cosmos transparent, allowing photons to travel freely. That light still travels today as the cosmic microwave background, a soft glow, a fossil imprint from when the universe was merely 380,000 years old. This ancient afterglow confirms a hot, dense origin, painting the sky with subtle ripples that tell the story of creation. Our confidence in the Big Bang theory is rooted in powerful evidence. The uniformity of the CMB observed across the sky points to a single fiery origin. Equally telling is the redshift of distant galaxies, discovered by Edwin Hubble, a sign that the universe is still expanding, stretching space and the light it carries. And the precise abundance of light elements forged in the universe's first minutes matches the predictions of Big Bang nucleosynthesis. These three pillars, CMB radiation, redshift, and element ratios, construct a clear, coherent narrative. The universe began with a bang, and everything that followed, from atoms to galaxies to life, shares that singular, ancient beginning. Yet in those early times, the universe was still a vast, dark expanse of hydrogen and helium. So how did it evolve into the intricate cosmos we see today? The answer lies in gravity. Tiny fluctuations in density, Remnants from inflation gave some regions a slight mass advantage. Gravity amplified these imperfections, drawing in more matter and initiating a long cascade of collapse. Over millions of years, gas clouds thickened and heated, eventually igniting nuclear fusion, the birth of the first stars. These population 3 stars were enormous, ephemeral giants made almost entirely of hydrogen and helium. Burning through their fuel rapidly, they exploded as supernovae, seeding the cosmos with the first heavy elements: carbon, oxygen, iron, the ingredients for life. These early supernovae were more than cosmic fireworks. They were forges, enriching interstellar clouds with newly minted elements. The process continued in cycles. New stars formed, lived, died, and scattered their ashes across space. Gradually, primitive galaxies emerged, turbulent cradles of star formation. Over billions of years, these galaxies grew larger and more structured, ultimately forming majestic spirals and massive ellipticals. Around 4.6 billion years ago, in one such enriched cloud, our Sun was born. Surrounding it, dust and gas coalesced into planets, including Earth, a once molten sphere that cooled, developed oceans, and nurtured the chemistry of life. Stars, far from being mere specks of light, are cosmic engines. They burn hydrogen into helium in a stable phase called the main sequence, balancing the inward pull of gravity with the outward push of radiation. A star's mass determines its fate. Small stars burn gently and live for billions of years. Massive stars shine fiercely, dying young in spectacular deaths. When fusion halts, smaller stars shed their outer layers, forming glowing planetary nebulae and leaving behind white dwarfs, dense stellar remnants. Massive stars meet a more dramatic end. When iron accumulates in their cores, an element that absorbs rather than releases energy during fusion, gravity wins. The core collapses violently, triggering a supernova. In the inferno of a supernova, elements heavier than iron, like gold and uranium, are born. Depending on mass, the leftover core becomes either a neutron star, unimaginably dense and spinning at breakneck speed, or a black hole, a gravity well so intense not even light can escape. These stellar deaths enrich the universe further. The iron in our blood, the calcium in our bones, and the oxygen we breathe all originated in ancient stars. Our solar system emerged from one such enriched cloud, a testament to the cosmic recycling that builds and rebuilds the universe. Earth began as a molten planet, gradually cooling and forming an atmosphere and oceans. Life followed, rising from simple molecules to complex beings. All of this, every tree, every thought, every heartbeat, is a result of nuclear fusion in long-dead stars. And yet, the cosmos continues to evolve. Galaxies merge, birthing new stars. Black holes grow, consuming matter and merging into titanic singularities. Somewhere, new solar systems are forming, perhaps even new Earths. As we peer into the night sky, we're not just seeing stars. We are witnessing the story of transformation, of matter becoming structure, of chaos becoming complexity. The universe, born from a tiny point of unimaginable energy, continues to expand, to evolve, and to invite questions. What lies beyond our cosmic horizon? Will the universe expand forever or collapse in a big crunch? Are there other universes, parallel realities beyond our own? To find answers, we must explore the mysteries of dark matter and dark energy, which comprise most of the universe, yet remain elusive. We must unlock the nature of singularities and quantum spacetime to glimpse the mechanics of the universe at its most fundamental. Every discovery brings us closer to the truth, but also reveals how much we do not yet understand. As we gaze upward, we realize the universe is not just a physical realm. It is a living story, unfolding moment by moment, and so long as we continue to seek, the story will never end. We are not merely seeing distant stars. We are witnessing the history of the universe itself. Every point of light is a reminder of the cosmic cycle of birth, life, and death that has been unfolding for billions of years. It is a story written in the language of light and matter, energy and time, a story that connects us to the stars themselves. The atoms in our bodies were forged in ancient stars that lived and died long before our sun was born. We are quite literally made of stardust. This realization not only deepens our understanding of the cosmos, but also our connection to it. The universe is a vast and complex web of energy, matter, and time, constantly evolving and changing. From the fiery birth of the first stars to the quiet fading of white dwarfs, from the violent explosions of supernovae to the mysterious depths of black holes, the cosmos is alive with creation and destruction. And as long as we continue to explore the stars to seek answers to the deepest questions of existence, the story of the universe will continue to unfold, one discovery at a time. Incredible force, releasing an immense amount of energy and scattering heavy elements across the universe. These elements, created in the intense heat and pressure of the supernova, include carbon, oxygen, iron, gold, and even uranium. Without these explosions, the universe would be a much simpler place, devoid of the complex chemistry needed to form planets, oceans, and life itself. Supernovae are not just dramatic endings, they are also beginnings. The shock waves from these cosmic blasts can travel across space, colliding with nearby gas and dust clouds. This collision compresses the gas, triggering the birth of new stars. In this way, supernovae help recycle matter, enriching the universe with the heavy elements necessary for life. But the story of a massive star's death doesn't end with the explosion. What remains after the outer layers are blown away depends on the mass of the core. If the core is between 1.4 and 3 times the mass of the Sun, it becomes a neutron star. These are incredibly dense objects made almost entirely of neutrons. A neutron star is so compact that a teaspoon of its material would weigh billions of tons. Neutron stars are not just dense, they are also magnetic powerhouses. Some neutron stars spin rapidly, emitting beams of radiation from their magnetic poles. If these beams are pointed toward Earth, we observe them as pulses of light, which is why they are called pulsars. Pulsars rotate with such precision that they rival atomic clocks, making them valuable tools for astronomers. However, if the core is even more massive, greater than 3 times the mass of the Sun, gravity wins the battle completely, and the core collapses into a black hole. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. It is an object of infinite density in zero volume, creating a point known as a singularity. Around this singularity is the event horizon, the point of no return beyond which nothing can escape the gravitational pull. Black holes are among the most mysterious objects in the universe. They warp space and time around them, distorting everything that passes nearby. Anything that crosses the event horizon is lost forever, adding to the black hole's mass. Black holes can grow by feeding on surrounding gas and stars, becoming even more massive over time. At the centers of most galaxies, including our own Milky Way, lie supermassive black holes, with masses millions or even billions of times greater than the Sun. These cosmic giants are thought to play a crucial role in the formation and evolution of galaxies. As they consume matter, they release enormous amounts of energy, shaping the galaxies around them. The deaths of massive stars through supernovae and black holes are cataclysmic events that reshape the universe. They create the heavy elements that make planets and life possible, and they trigger the birth of new stars and solar systems. Without them, the universe would be a much simpler and lifeless place. But the life cycle of stars is not just about death and destruction, it's also about renewal and creation. The gas and dust ejected from dying stars are recycled into new generations of stars and planets. This cosmic recycling has been going on for billions of years, creating a universe rich in complexity and diversity. Our own Sun is part of this grand cycle. It was born from a cloud of gas and dust, enriched by earlier generations of stars around 4.6 billion years ago. This cloud collapsed under gravity, forming the Sun at its center. The remaining material flattened into a rotating disk, from which the planets, moons, asteroids, and comets of our solar system formed. Earth, one of these newborn planets, began as a molten ball of rock. Over millions of years, it cooled, developed an atmosphere, and accumulated oceans, setting the stage for the emergence of life. The elements that make up our bodies, carbon, oxygen, nitrogen, and iron, were forged in ancient stars that lived and died long before the sun was born. We are quite literally made of stardust. Every atom in our bodies was created in the hearts of dying stars and scattered across the cosmos by supernovae. This profound connection to the universe unites us with the stars, the galaxies, and the cosmos itself. The life cycle of stars, from birth in stellar nurseries to death in supernovae or collapse into black holes, is a continuous process of creation and transformation. It is a story of balance and change, of destruction and rebirth, that shapes the universe and makes life possible. Stars are the engines of the universe. They forge the elements, light up the galaxies, and create the conditions for life. And even in death, they continue to shape the cosmos, spreading their enriched materials across space to create new stars and worlds. As we look up at the night sky, we are not just seeing stars, we are witnessing the history of the universe itself. Every point of light is a reminder of the cosmic cycle of birth, life, and death that has been unfolding for billions of years. It is a story written in the language of light and matter, energy and time, a story that connects us to the stars and the universe as a whole. The cosmos is alive with creation and destruction, from the fiery birth of stars to the explosive deaths of supernovae, from the quiet fading of white dwarfs to the mysterious depths of black holes. The universe is a vast and complex web of energy and matter, constantly evolving and changing, and as long as we continue to explore the stars, to seek answers to the deepest questions of existence, the story of the universe will continue to unfold, one discovery at a time. Like stars and planets, dark matter, however, does not interact with electromagnetic forces, which means it cannot emit light, heat, or radiation. Without a way to lose energy, dark matter particles remain in fast random motions, preventing them from clumping together to form dense structures, instead of forming objects like stars. Dark matter exists as large, diffuse halos surrounding galaxies, contributing to their gravitational mass, but not participating in normal matter interactions. Additionally, dark matter does not interact strongly with itself. Unlike regular matter, which can collide and stick together, dark matter particles pass through each other and normal matter almost without resistance. This lack of interaction further prevents dark matter from forming compact objects. The inability of dark matter to cool and clump also has profound implications for the formation of galaxies and large-scale structures in the universe. While normal matter can collapse into stars and galaxies, dark matter forms a vast, invisible scaffold around which galaxies can form. The gravitational pull of dark matter draws in regular matter, allowing galaxies to develop within these dark matter halos. The cosmic web, a large-scale structure of the universe, is also influenced by dark matter. This web consists of vast filaments of galaxies connected by threads of dark matter with enormous voids in between. The distribution of dark matter helps shape this structure, guiding the formation of galaxies and clusters along these filaments. Despite its elusiveness, the effects of dark matter are evident through gravitational lensing. When a massive object like a galaxy cluster lies between a distant light source and an observer, its gravity bends the light, distorting the image of the source. By studying these distortions, scientists can map the distribution of dark matter, revealing its presence even though it is invisible. Experiments to detect dark matter directly are ongoing. These include attempting to observe dark matter particles interacting with normal matter in underground detectors, searching for dark matter particles in high-energy collisions at particle accelerators, and looking for evidence of dark matter particles annihilating each other in space. However, no definitive detection has yet been made. The search for dark matter is one of the most significant challenges in modern physics. Solving this mystery could lead to a deeper understanding of the universe's composition, the nature of gravity, and possibly reveal new particles and forces of nature. In the grand scheme of the universe, dark matter plays a vital role. It affects the rotation of galaxies, the formation of large-scale structures, and the behavior of the universe on the grandest scale. Yet it remains one of the biggest enigmas of our time, an unseen but potential player in the cosmic story. As we continue to explore the universe through telescopes, particle detectors, and advanced simulations, we edge closer to unraveling the mystery of dark matter. Each discovery, whether it supports or challenges our current theories, brings us closer to a deeper and more complete understanding of the cosmos. Lensing patterns that match predictions made by modified Newtonian dynamics, MOND. However, these successes are exceptions rather than the rule. Most alternative theories struggle to account for the full range of evidence supporting dark matter, such as cosmic microwave background radiation, galaxy rotation curves, and the large-scale structure of the universe. One of the most prominent alternatives to dark matter is MOND, which was proposed by physicist Mordechai Milgrom in the 1980s. MOND modifies Newton's laws of motion to explain galaxy rotation curves without requiring dark matter. According to MOND, at extremely low accelerations like those found at the outer edges of galaxies, gravity behaves differently than predicted by Newton or Einstein. This modification successfully explains the flat rotation curves observed in galaxies. However, MOND struggles to explain other phenomena, such as gravitational lensing and the distribution of dark matter in galaxy clusters. A more recent extension of MOND is called TeVS, Tensor Vector Scalar Gravity, proposed by Jacob Bekenstein. TeVS is a relativistic version of MOND that attempts to reconcile the theory with general relativity. It introduces additional fields to modify gravity at large scales, preserving the successes of MOND while aiming to explain gravitational lensing. Despite some promising results, TeVS is complex and introduces new parameters, leading to questions about its simplicity compared to the dark matter hypothesis. Another alternative is FR gravity, which modifies Einstein's general relativity by altering the function that describes the relationship between space-time curvature and matter. This approach can produce effects similar to dark matter on galactic and cosmic scales. However, FR gravity introduces additional complications and has difficulty matching observations of the cosmic microwave background and galaxy clustering. Negative mass theories propose that the universe contains particles with negative mass, which would repel regular matter. These particles would create gravitational effects similar to dark matter. However, negative mass is a highly speculative concept that contradicts known physics and has not been observed experimentally. Dark fluid theory suggests that dark matter and dark energy are two aspects of a single substance, which behaves like dark matter in galaxies and like dark energy on cosmic scales. This theory attempts to unify the explanation for both phenomena, but remains largely theoretical without strong observational support. Entropic gravity, proposed by Erik Verlinde, suggests that gravity is an emergent phenomenon arising from the thermodynamics of information stored in space-time. This approach explains galaxy rotation curves without dark matter by modifying the behavior of gravity at large scales. While intriguing, entropic gravity is still in development and faces challenges in explaining galaxy clusters and the cosmic microwave background. While these alternative theories are imaginative and provide novel insights into gravity and cosmology, they face significant challenges. They must not only explain the observations attributed to dark matter, but also remain consistent with the well-tested predictions of general relativity and quantum mechanics. Most of these alternatives fail to fully account for all the evidence, including the cosmic microwave background, gravitational lensing, and the large-scale structure of the universe. Meanwhile, the dark matter hypothesis remains the most widely accepted explanation for the unseen mass influencing galaxies and cosmic structures. It is supported by a wide range of observations, including galaxy rotation curves that remain flat at large distances from the center, gravitational lensing that reveals more mass than can be accounted for by visible matter, the cosmic microwave background which shows patterns consistent with the influence of dark matter on early universe density fluctuations, the distribution of galaxies, and the formation of cosmic structures which require the gravitational pull of dark matter. The search for dark matter continues, with increasingly sophisticated experiments. Direct detection experiments seek to observe dark matter particles interacting with normal matter in underground detectors. Indirect detection looks for signals of dark matter annihilation or decay in space, such as gamma rays or neutrinos. Particle accelerators like the Large Hadron Collider aim to produce dark matter particles in high-energy collisions. Despite the lack of direct detection so far, the consistency of the dark matter hypothesis across multiple lines of evidence makes it the leading explanation for the missing mass in the universe. The search for dark matter is one of the most exciting frontiers in physics, with the potential to reveal entirely new particles and forces of nature. In the grand tapestry of the universe, dark matter remains an invisible but essential thread. It shapes galaxies, guides cosmic structures, and holds the key to understanding the full composition of the cosmos. As we continue to explore the universe with advanced telescopes, detectors, and particle accelerators, we move closer to solving one of the greatest mysteries of modern science: the true nature of dark matter. Some observations suggest that dark energy's influence might have changed over time, possibly supporting the idea of dynamic scalar fields like quintessence. Future prospects and observations ongoing in upcoming observational missions aim to shed more light on dark energy's nature. Euclid Space Telescope, ESA designed, will map the geometry of the dark universe, helping to constrain dark energy models. Vera C. Rubin Observatory will conduct deep sky surveys to study dark energy through supernovae, BAO, and gravitational lensing. Nancy Grace Roman Space Telescope, NASA, will provide high-precision measurements of cosmic expansion and dark energy's effects. Conclusion: the quest continues. Dark energy remains one of the most profound mysteries in modern cosmology. Its discovery revolutionized our understanding of the universe, leading to the realization that we know very little about the majority of its contents. Whether it is a cosmological constant, a dynamic scalar field, a manifestation of modified gravity, or something entirely new, solving the mystery of dark energy will likely require a paradigm shift in physics. As astronomers and physicists continue to explore the cosmos with increasingly advanced tools and techniques, we move closer to unveiling the true nature of dark energy. Whatever the answer, it will not only reshape our understanding of the universe, but also provide deeper insights into the fundamental laws of nature itself. The expanding universe, unraveling the mystery of dark energy. The universe's expansion has fascinated scientists for decades. Recent measurements using innovative techniques have revealed that galaxies up to 2 billion parsecs away show evidence of the universe expanding faster over time. This accelerating expansion is one of the strongest pieces of evidence for the existence of dark energy, a mysterious force that makes up approximately 68% of the universe. The need for dark energy in a flat universe. Observations indicate that the universe is flat, meaning its total energy density is precisely balanced between gravitational collapse and endless expansion. However, regular baryonic matter and dark matter combined only account for about 30% of the needed energy. The remaining 70% must come from an unknown source, what we call dark energy. Early data from the Wilkinson Microwave Anisotropy Probe WMAP suggested that dark energy made up 72.8% of the universe, but more precise measurements from the Planck spacecraft have refined this to 68.3%, with dark matter at 26.8% and regular matter at just 4%. Cosmic microwave background and the ISW effect. The integrated Sachs-Wolf ISW effect provides further evidence for dark energy. When photons from the cosmic microwave background CMB travel through large-scale structures like galaxy clusters or voids, they gain or lose energy, creating distinct hot and cold spots in the background radiation. This effect aligns well with the presence of dark energy influencing the universe's structure and expansion. New methods to measure dark energy. Scientists have developed innovative methods to study dark energy, including using the Hubble constant to track the universe's expansion over time. By analyzing passively evolving galaxies as cosmic clocks, researchers can measure their ages and redshifts to directly estimate how fast the universe expanded at different points in its history. The mystery of dark energy. What could it be? Despite mounting evidence for dark energy's influence, its true nature remains elusive. The simplest theory is that dark energy is a fundamental property of space itself, often described as vacuum energy. According to this idea, empty space is not truly empty, but filled with a type of energy that affects the universe's expansion. This concept aligns with the cosmological constant, denoted by the Greek letter lambda, a term introduced by Einstein in his general theory of relativity. However, a major problem arises with this theory. Quantum physics predicts an enormous amount of vacuum energy, 120 orders of magnitude more than what we observe. If this prediction were accurate, the universe would have expanded so rapidly that galaxies, stars, and planets could never have formed. The fact that the universe exists as it does suggests that most of this vacuum energy is somehow cancelled out, but scientists do not yet understand why. Alternative theories, quintessence and beyond.
Not all physicists believe dark energy is a constant force. Some propose it could be a dynamic, evolving energy field known as quintessence. Unlike the cosmological constant, quintessence can change over time and space, acting like a field that influences the universe's expansion in a more complex way. This theory allows for dark energy to vary, potentially explaining why it became dominant in the current era of cosmic history.
Phantom energy and the Big Rip. Some extreme quintessence models predict even stranger scenarios. Phantom energy, for instance, could increase over time, eventually tearing apart galaxies, stars, planets, and even atoms in a dramatic event called the Big Rip. Quiescence.
Another theory, quiescence, involves unusual forms of energy that could have negative kinetic energy, leading to unpredictable effects on the evolution of the cosmos.
The Hubble tension and the future of dark energy research. A recent challenge in cosmology is the Hubble tension, a discrepancy in the measurements of the universe's expansion rate. The rate observed using the CMB differs from that calculated using Type 1a supernovae. Some scientists believe this inconsistency might indicate that only certain types of quintessence models are viable, possibly involving additional interactions between dark energy and other forces. Modifying gravity. Could it replace dark energy? An alternative approach to explaining cosmic acceleration involves modifying Einstein's theory of general relativity. Some modified gravity theories propose that the accelerated expansion of the universe might be a natural result of how gravity works on large scales, eliminating the need for dark energy altogether. However, a critical discovery in 2017, the measurement of gravitational waves from the GW17 event, ruled out many of these alternative theories, strengthening the case for dark energy as a genuine phenomenon. How dark energy took over the universe. Scientists estimate that the universe's expansion began accelerating around 5 billion years ago. Before this period, the gravitational pull of dark matter and regular matter was strong enough to slow the expansion. However, as the universe expanded, matter spread out and became less influential, while dark energy remained nearly constant. Eventually, dark energy's influence surpassed gravity, leading to the accelerated expansion we observe today. The ultimate fate of the universe. Scenarios driven by dark energy. The fate of the universe depends largely on the nature of dark energy. Endless expansion. If dark energy remains constant, as predicted by the cosmological constant model, the universe will continue expanding forever. Galaxies beyond our local group will drift away, eventually moving faster than the speed of light relative to us. These galaxies will fade from view, leaving an isolated dark cosmos. The Big Rip. If dark energy increases over time, the universe could end in the Big Rip, where the force of expansion becomes so powerful that it destroys all structures down to the atomic level. The Big Crunch. Alternatively, if dark energy reverses its effect, it could lead to a big crunch, where the universe's expansion halts and reverses, causing everything to collapse back into a singularity. Cyclic model. Some theories suggest the universe might undergo endless cycles of expansion and contraction, with each Big Bang followed by a big crunch. Dark energy's role in the early universe and beyond. The timeline of the universe's history shows that dark energy was not always dominant. During the first few 100,000 years, matter and radiation shaped the cosmos. It was only after the formation of galaxies and large-scale structures that dark energy began to take over, accelerating the universe's expansion. Dark energy remains one of the greatest unsolved mysteries in physics. Its discovery has transformed our understanding of the cosmos, revealing that the universe is not just expanding but doing so at an ever-increasing rate. Whether dark energy is a fundamental aspect of space, a dynamic force like quintessence, or an indicator of new physics beyond our current theories, it continues to challenge and inspire cosmologists and physicists worldwide. As technology advances and new observational techniques are developed, the hope is that future discoveries will bring us closer to uncovering the true nature of dark energy. Whatever the answer, it promises to deepen our understanding of the universe and our place within it, opening new horizons for both science and human curiosity. The distant future, the end of the Stelliferous era and the fate of the universe. In the far reaches of time, the Stelliferous era, the age of star formation, will eventually conclude. This will occur when the birth of new stars ceases, leaving the universe to continue its relentless expansion. As this expansion persists, only the galaxies closest to us will remain observable, with the rest receding beyond the cosmic horizon. The ultimate fate of the universe, a mystery yet to be solved. The destiny of the universe remains one of the most profound mysteries in cosmology, with several potential scenarios still under consideration. By studying the current state of the cosmos, scientists hope to better predict its future. The observable expansion of the universe led to the formulation of the Big Bang theory, which proposes that the cosmos originated from an extremely hot and dense state, the lambda-CDM model. The leading explanation, an enhanced version of the Big Bang theory known as the lambda-cold dark matter, LaCDM model, aligns closely with a broad spectrum of astrophysical observations. This model traces the universe's expansion backward to incredibly high temperatures and densities. However, as we approach the earliest moments, where temperatures and densities become infinite, current physical models break down. The limitations of current models. The breakdown at infinite temperature. When tracing cosmic expansion backward, we encounter a point where temperature becomes infinite, or the scale factor approaches zero, effectively marking the beginning of time. At this juncture, our physical theories cease to be applicable. This paradox indicates that postulating an initial gravitational singularity is beyond the scope of present-day physics. The Planck epoch, where physics breaks down. According to the standard cosmological model, the universe has been expanding since it was in an extremely hot state. When we trace this expansion back to the Planck length, a minuscule distance where quantum effects dominate, the familiar laws of physics lose their validity. In this realm, energy levels become so extreme that quantum gravitational effects override Einstein's equations of general relativity. The Grand Unification Epoch, a time of immense heat and energy. Following the Planck era, the universe may be modeled using extensions of the standard model of particle physics, such as grand unified theories, GALOTS. However, no GALOT has yet matched current observations. In the first septillionth of a second after the Big Bang, the universe experienced the Grand Unification Epoch, marked by temperatures exceeding quadrillion giga-electron volts. Cosmic inflation, the universe's rapid expansion. One of the most crucial phases in the universe's development was cosmic inflation, a rapid expansion that occurred between 10^-pro and 10^-pro seconds after the Big Bang. During this fraction of a second, the universe expanded by at least a sextillion times its original size, smoothing out any irregularities and laying the foundation for the large-scale structures we observe today. The mystery of cosmic inflation. The driving force behind this dramatic expansion is not yet fully understood. A popular hypothesis suggests that inflation began when the strong nuclear force separated from the electroweak force, creating a field known as the inflaton field. During recombination, ionized particles like electrons and protons combined to form the first neutral atoms. Photon decoupling occurred when photons, previously trapped by constant interactions with charged particles, were finally able to travel freely as atoms reached stable energy states. Before recombination, the universe was incredibly hot. and filled with ionized plasma. Photons constantly collided with charged particles, preventing light from traveling far and rendering the universe opaque, almost like a cosmic fog. While light existed, it couldn't penetrate the dense plasma to create a clear view of the cosmos. As the universe continued to cool, starting around 18,000 years after the Big Bang, electrons began to bind with helium nuclei, leading to the formation of neutral helium atoms. By about 100,000 years, neutral hydrogen atoms began to appear as well. This initial combination of electrons and nuclei, referred to as recombination, wasn't a process, but rather the first instance of these particles coming together. Approximately 100,000 years later, the universe had cooled enough for the first molecule, helium hydride, to form. This molecule played a crucial role in early molecular chemistry. In 2019, scientists confirmed the existence of helium hydride in space, within the planetary nebula NGC 7027. This molecule eventually reacted with atomic hydrogen, leading to the creation of molecular hydrogen, the essential component for star formation. When hydrogen atoms combined in their low-energy state, they weren't very efficient. Typically, they held on to their high-energy electrons, and as they combined, these electrons would release energy, dropping to lower energy states and emitting photons in the process. This release of photons is known as photon decoupling. While some of these photons were absorbed by other hydrogen atoms, many remained free. By the time recombination concluded, most protons in the universe had combined with electrons to create neutral hydrogen atoms. This transition significantly increased the distance photons could travel without being absorbed, making the universe transparent to light, radio waves, and other electromagnetic radiation for the first time. The photons released during this era had a temperature of around 4000 K, which to the human eye would have appeared as a soft white light with a warm yellow or orange hue. Over billions of years, as the universe expanded, these photons stretched into longer wavelengths, transitioning from visible light to microwave radiation at about 2. This process, called redshifting, is due to the universe's expansion, which elongates photon wavelengths and reduces their frequency. These redshifted photons are still detectable today as radio waves, contributing to what we know as the cosmic microwave background, CMB. The CMB offers a valuable glimpse into the early universe, preserving evidence of its development and the conditions shortly after the Big Bang. Around the same period as recombination, pressure waves within the electron-baryon plasma became embedded in the universe's matter distribution as it began to condense. These pressure waves, known as baryon acoustic oscillations, left behind subtle patterns in the large-scale structure of the cosmos. The cosmic microwave background serves as a snapshot of the universe at the end of this era, showcasing the slight fluctuations present from the earliest moments of cosmic inflation. The distribution of galaxies observed today reflects the universe's scale and evolution over time. Despite the universe becoming transparent following recombination and decoupling, it remained too cool for stars or galaxies to form immediately. It wasn't until gravity began to pull together denser regions of gas, over hundreds of millions of years, that stars and galaxies started to emerge. This delay explains why stars only began shining long after recombination. The universe entered a phase known as the Dark Ages around 370,000 years after the Big Bang. During this time, temperatures dropped from approximately 4,000 K. The only photon sources were those emitted during recombination, which we now observe as the CMB, and photons sporadically released by neutral hydrogen atoms through a process known as the 21 centimeter spin line, which falls within the microwave frequency range. Within just 3 million years, the CMB photons had shifted out of visible light into the infrared spectrum. For a long period, the universe remained without visible light, experiencing true darkness until the first stars ignited. These early stars, known as population 3 stars, began to form a few hundred million years after the Big Bang, casting the first visible light and signaling the end of the Dark Ages. As structures gradually took shape, Early galaxies started to appear between 80 and 700 million years after the Big Bang. This slow evolution continued, and by approximately 1 billion years after the Big Bang, the universe began to resemble its current state. The oldest stars and galaxies observed today formed just after the onset of reionization, a process that began around 400 million years post-Big Bang. In 2016, the Hubble Space Telescope observed galaxies like GN-ZL11, dating to about 400 million years after the Big Bang. The more advanced James Webb Space Telescope, launched in December 2021, can detect galaxies up to 100 times fainter than Hubble, potentially revealing objects from as early as 18 million years post-Big Bang, possibly even earlier than the first galaxies. Scientists are also investigating a faint form of radiation known as the 21 centimeter spinline radiation, which may offer deeper insights into the early universe than the CMB. By studying this radiation, researchers hope to refine our understanding of when the first stars, galaxies, black holes, and quasars emerged, and to pinpoint the precise timing of the reionization period. Overall, our understanding of the universe's early stages continues to evolve with new discoveries and technologies. Each finding helps piece together the vast and complex puzzle of how the cosmos transformed from a dark and featureless expanse into the vibrant and dynamic universe we see today. The Casimir effect. In 1947, Dutch physicists Hendrik Casimir and Dirk Polder conducted a groundbreaking experiment that led to the discovery of what is now known as the Casimir effect. They placed two uncharged metal plates extremely close together inside a vacuum. According to classical physics, nothing significant should have occurred. However, to their astonishment, the plates mysteriously moved toward each other, as if an invisible force was drawing them together. The cause of this force was traced to quantum fluctuations. The narrow space between the plates was so small that certain quantum energy fluctuations were suppressed, leading to an imbalance in pressure between the inside and the outside of the plates. This imbalance created an attractive force, demonstrating that even in a vacuum, there is something present, something invisible yet undeniably real. The Casimir effect was revolutionary because it provided concrete evidence that empty space is far from empty. It confirmed that the vacuum itself contains energy, fundamentally altering our understanding of physics and the nature of reality. But this discovery raised even more profound questions. If empty space is filled with quantum fluctuations, could these tiny bursts of energy have played a role in the creation of the universe itself?